This is my Lab 5 for Physics 2211, and the objective of this lab was to observe two objects that fall at different rates, one quickly and one slowly. Then we were to construct a model based on only the force of gravity, and then incorporating the force of drag and gravity into a different model. The results that I received was that the faster dropping object has a smaller coefficient of proportionality, the slower falling object is affected more by drag and reach terminal velocity more quickly. Terminal velocity for viscous drag is force of gravity over b, because this is where bv is equal to force of gravity. So F net is equal to 0, and b is the coefficient of proportionality. The two objects I chose to observe was a small soccer ball and a paper cone. The beginning of the period is right when I let go, and the ending of the observation period is right before the ball hits the ground. The average location that I chose was the furthest point of the object that was in the frame. So for the ball, this is an example, and for the paper, this is an example. The direction of movement of the ball and piece of paper is the negative y direction. The origin is where the center of the ball, right at the beginning of the observation period. The distance between the change in time between each frame is 0.042 seconds, so 24 frames per second. The diameter of the ball was the length that I used, and it was 0.12 meters. If you notice these two plateaus here, those were frames that had no change, and they were just lag frames, I guess. So those were taken out of the data. So let's look at the model. So the model for the ball here is that I set the mass equal to the mass of the ball, 0.12 kilograms. Initial position is the initial position of the tracker, so negative 0.056 meters. The time period is the same as the observation period, so 0.458. Here I just have gravity equal to the mass times g, which is 9.81 times negative 1, so it's going negative y direction. And so I have drag here set to 0, so this is just F net is equal to F drag plus 0. Velocity is just the momentum principle, where each component is divided by the mass. And position is just determined by the final position is equal to initial position plus the velocity for a small time period. So let's run this. This is without drag. So this is just what we would expect from the last lab. Let's incorporate in drag. So drag here is equal to negative b times the change in velocity. So what that means is that I took the direction, the unit vector in the direction, so that's the velocity over speed, and once you multiply this times speed, since it's proportional to speed, the two speeds cancel out, so you just get negative b times velocity. I multiplied by it, and F net is just equal to the force of gravity plus force of drag. So let's run this. There's not really a change. It's not really changed because the constant proportionality is so tiny. So let's look at the model for paper. It's the same, but mass is changed to 0.0025. Initial position is changed to 0 and negative 0.086. So the constant proportionality is also different. So this is without drag first. So it's basically the same as the ball, but if we incorporate drag into the model, it starts going in a straight line. As you can see, the drag, force of drag is beginning to be equal to the force of gravity. So let's see how this matches up in Excel. So the ball, there's not really a difference between the two models because the force of drag is so tiny. But for the paper, the model with drag is much better estimate because the change in velocity begins to equal 0, so velocity becomes constant, and as you can see here, it doesn't increase like the ball. So I produced these two graphs with my model. This is the one without drag, this is with drag, and this is velocity. So as you can see, the one with drag does reach terminal velocity where velocity is constant, while the other one, it continues to increase. For the what if question, this is the thrown down without drag, continues to increase, but the one that has drag actually decreases to reach terminal velocity, the same terminal velocity as in the other graph.